In electrical systems involving transformers, the presence of a neutral conductor plays a crucial role in managing harmonic currents. Consider a scenario where a pad-mounted transformer steps down voltage from 12,470 volts delta to 480 volts Y, and this 480 volts Y output feeds another transformer that further steps down the voltage to 208/120 volts Y. In such a configuration, the question arises whether a neutral connection should be maintained between the two transformers, especially when the secondary side of the second transformer derives its own neutral. The answer is definitively yes, the neutral connection should not be omitted. The primary reason for maintaining the neutral connection lies in its function as a return path for harmonic currents. Transformers, particularly those serving nonlinear loads, generate harmonic currents. These harmonic currents are integer multiples of the fundamental frequency, which is typically 60 Hz in North America. Nonlinear loads, such as electronic devices, computers, and variable frequency drives, draw current in a non-sinusoidal manner, leading to the production of harmonic currents. These harmonic currents can circulate within the electrical system and, if not properly managed, can cause a range of problems. Without a dedicated neutral conductor, harmonic currents can find alternative paths to return to the source, often through grounding conductors or other unintended pathways. This can lead to increased current flow in these unintended paths, causing overheating, voltage distortion, and equipment malfunction. The neutral conductor provides a low impedance path for harmonic currents to flow back to the source, mitigating these issues. By providing a dedicated return path, the neutral conductor minimizes the circulation of harmonic currents through other parts of the electrical system, reducing the risk of overheating, voltage distortion, and equipment damage. In the specific scenario described, where a 480 volts delta to 208/120 volts Y transformer derives its own neutral on the secondary side, the presence of a neutral connection between the two transformers is still essential. The neutral on the secondary side primarily serves to provide a balanced voltage reference for the 208/120 volts Y system, ensuring that the voltage between each phase and neutral is consistent. However, it does not eliminate the need for a neutral connection between the transformers to handle harmonic currents generated by the primary side. If the neutral connection between the transformers is removed, harmonic currents generated by the primary side can circulate through the grounding system, potentially causing ground loops and other issues. This can lead to increased noise in the electrical system, interference with sensitive electronic equipment, and even safety hazards. Furthermore, the absence of a neutral connection can place undue stress on the transformer itself. Harmonic currents can cause increased heating within the transformer windings, reducing its lifespan and potentially leading to premature failure. The increased heating can also degrade the insulation within the transformer, increasing the risk of short circuits and other faults. In addition to protecting the transformer and other equipment, maintaining the neutral connection also improves the overall power quality of the electrical system. By providing a dedicated return path for harmonic currents, the neutral conductor helps to minimize voltage distortion and maintain a stable voltage supply. This is particularly important for sensitive electronic equipment that is susceptible to voltage fluctuations and harmonic distortion. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems, including requirements for neutral conductors. While the specific requirements may vary depending on the application and voltage level, the general principle is to ensure that a low impedance path is provided for fault currents and harmonic currents to return to the source. Article 250 of the NEC covers grounding and bonding requirements, including the sizing and installation of neutral conductors. It is important to consult the NEC and other relevant standards to ensure that the electrical system is properly grounded and bonded. Proper grounding and bonding practices are essential for ensuring the safety and reliability of the electrical system. Grounding provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and de-energize the circuit. Bonding ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electric shock. In addition to the NEC, other standards and guidelines may also apply, such as those published by the Institute of Electrical and Electronics Engineers, or IEE. The IEE provides guidance on power quality issues, including harmonic mitigation techniques. Various methods can be employed to mitigate harmonic currents, such as using harmonic filters, reactors, or active harmonic correction devices. Harmonic filters are designed to block or reduce the flow of harmonic currents, while reactors can be used to limit the magnitude of harmonic currents. Active harmonic correction devices use electronic circuitry to cancel out harmonic currents, providing a more comprehensive solution. The selection of the appropriate harmonic mitigation technique depends on the specific characteristics of the electrical system and the types of loads being served. It is important to conduct a thorough harmonic analysis to identify the sources and magnitudes of harmonic currents before implementing any mitigation measures. In summary, the neutral connection between transformers should not be omitted, as it provides a crucial return path for harmonic currents. The absence of a neutral connection can lead to a range of problems, including increased heating, voltage distortion, equipment malfunction, and safety hazards. Proper grounding and bonding practices, along with appropriate harmonic mitigation techniques, are essential for ensuring the safety, reliability, and power quality of the electrical system. Always consult the NEC and other relevant standards when designing and installing electrical systems to ensure compliance with applicable codes and regulations. When dealing with electrical systems, safety should always be the top priority. Working with electricity can be dangerous, and it is important to take precautions to protect yourself from electric shock and other hazards. Always de-energize circuits before working on them, and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not qualified to work on electrical systems, it is best to hire a licensed electrician to perform the work. Electricity is a powerful force, and it should be treated with respect. Understanding the principles of electrical systems, including the importance of neutral conductors and grounding, is essential for ensuring the safe and reliable operation of electrical equipment. By following proper practices and adhering to applicable codes and standards, you can minimize the risk of electrical hazards and ensure that your electrical system operates efficiently and safely. Moreover, consider the role of the neutral in three-phase Y systems. In these systems, the neutral point is the common connection of the three-phase windings, and it is typically grounded. The neutral conductor carries any unbalanced current that may be present in the three phases. Without a neutral conductor, unbalanced loads can cause voltage imbalances and other problems. Voltage imbalances can lead to increased current flow in some phases and decreased current flow in others, resulting in overheating and equipment damage. In addition to carrying unbalanced currents, the neutral conductor also provides a reference point for the phase voltages. The phase voltages are measured with respect to the neutral point, and they should be equal in magnitude and 120 degrees apart in phase. If the neutral point is not properly grounded, the phase voltages can become distorted and unbalanced, leading to various problems. Voltage distortion can interfere with the operation of sensitive electronic equipment, causing malfunctions and errors. Imbalanced voltages can also cause increased stress on motors and other rotating equipment, reducing their lifespan. To ensure proper grounding of the neutral point, it is common to use a grounding electrode conductor, which is connected to a grounding electrode, such as a ground rod or a grounding plate. The grounding electrode provides a low impedance path to ground, allowing fault currents to flow back to the source and trip over current protection devices. The size of the grounding electrode conductor is typically determined by the size of the service entrance conductors, as specified in NEC. In addition to grounding the neutral point, it is also important to bond all metallic parts of the electrical system together. Bonding ensures that all metallic parts are at the same potential, reducing the risk of electric shock. Bonding conductors are typically used to connect metallic enclosures, raceways, and other metallic parts to the grounding system. The size of the bonding conductors is also specified in the NEC. Proper grounding and bonding practices are essential for ensuring the safety and reliability of electrical systems. By providing a low impedance path for fault currents and harmonic currents, grounding and bonding help to protect people and equipment from electrical hazards. Additionally, consider the impact of harmonic currents on power factor. Harmonic currents can reduce the power factor of the electrical system, which is a measure of how efficiently electrical power is being used. A low power factor can result in increased energy costs and reduced system capacity. To improve the power factor, it is common to use power factor correction capacitors. Power factor correction capacitors are designed to counteract the effects of inductive loads, such as motors and transformers, which tend to lower the power factor. By adding power factor correction capacitors to the electrical system, it is possible to improve the power factor and reduce energy costs. In addition to power factor correction capacitors, other techniques can also be used to improve the power factor, such as using synchronous motors or active power factor correction devices. The selection of the appropriate power factor correction technique depends on the specific characteristics of the electrical system and the types of loads being served. It is important to conduct a thorough power factor analysis to identify the causes of low power factor before implementing any correction measures. Moreover, think about the role of surge protection devices. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, which can be caused by lightning strikes, switching events, or other disturbances. Voltage surges can damage or destroy sensitive electronic equipment, leading to costly repairs or replacements. SPD work by diverting surge current to ground, preventing it from reaching the protected equipment. SPD are typically installed at the service entrance of the building and at other strategic locations throughout the electrical system. There are different types of SPD available, each with different voltage ratings and surge current capacities. The selection of the appropriate SPD depends on the specific characteristics of the electrical system and the level of surge protection required. It is important to install SPD in accordance with the manufacturer's instructions and to ensure that they are properly grounded. Proper grounding is essential for the effective operation of SPD. In addition to SPD, other surge protection measures can also be implemented, such as using shielded cables and surge-protected power strips. Shielded cables help to reduce the amount of surge current that can enter the electrical system, while surge-protected power strips provide additional protection for individual pieces of equipment. Furthermore, be cognizant of the importance of regular maintenance and testing. The electrical system should be regularly inspected and tested to ensure that they are operating safely and efficiently. Regular maintenance can help to identify potential problems before they become serious, preventing costly repairs or replacements. Maintenance tasks can include inspecting wiring, tightening connections, testing overcurrent protection devices, and measuring voltage and current levels. Testing can include insulation resistance testing, ground resistance testing, and harmonic analysis. Insulation resistance testing is used to check the condition of the insulation on wires and cables. Ground resistance testing is used to measure the resistance of the grounding system. Harmonic analysis is used to identify the sources and magnitudes of harmonic currents in the electrical system. The frequency of maintenance and testing should be determined based on the type of electrical system, the operating environment, and the manufacturer's recommendations. It is important to keep records of all maintenance and testing activities, including the dates, the results, and any corrective actions taken. These records can be used to track the performance of the electrical system and to identify any trends or patterns that may indicate potential problems. Skilled personnel should perform maintenance and testing tasks. If you are not qualified to perform these tasks, it is best to hire a licensed electrician or a qualified electrical contractor. Remember to prioritize safety.